computer, that's why. I'm sorry. Okay. So, good morning to everyone. I'm Mehdi Messaoudi, ESR number 5, a student at Università Politecnico di Valencia. And today I'm going to present novel technologies for miniaturized passive component with tuning capabilities. So, as we can see from the index, I'm going to start by explaining in general the characteristics that filter for space application must have. Then why CU technology can be a good choice. Then we move on tunable filter with a brief research market, following by CU technology and more precisely coaxial CU technology with 2 examples of projects that I worked on. One is a miniaturized filter, and another one is the reconfigurable one with varactors, and finally the conclusion. So here, the slide with the features that a filter must have in space. A satellite, once landed into space, must guarantee a substantial lifetime, which justifies the resource that we use for the creation and use. So the cost, the integrability, reliability, and the size are of vital importance. And moreover, as it's easy to imagine, the power consumption is also very important, as the losses. Another aspect to take into account is the possibility and the cost for the mass production, and all these features are obviously interlinked. So in this slide, we can see the comparison of technology. Well, the first thing to do, as in general in any project, is to identify which technology can best meet all the demands in the field of filter, as well as in almost any application. Frequently, we have to reach a kind of compromise. Coaxial filter are currently used as a standard technology in the realization of L and S-band filter. They are used for their flexibility in the bandwidth, from narrower filter to octave bandwidth with excellent performance. However, this technology is too large and bulky, so it's necessary to find, as I said, a trade-off between spurious performance, loaded quality factor, and assembly and specification. Coaxial substrate integrated waveguide can be a solution, a good compromise. Here we can see 3 main technology: microstrip, CU, and classical waveguide. Compared to the planar technology, such as microstrips, we has a higher quality factor. They are cheaper than the classical waveguide, even by the fact that they are fabricable with standard technology as LTCC or PCB. So CU technology replaces ideal metal walls with metallized vias that connects the upper conductor plane to the lower ground plane. So we are recreating like a waveguide with a few small losses. And the waves are confined into the substrate. So the choice of the substrate is of a great importance in this technology. The main losses are from the conductor loss that are due to the conductor, and the thickness here play a fundamental role. In fact, more we increase it, the lower is the attenuation cost of the conductor. And also radiaton leakage is minimized by reducing the diameter of the pathway. Here we can see some example of reconfigurable and tunable filters. Tunable filters needs a high quality factor because of losses due to the tuning elements, where they are becoming increasingly important in the recent year because they can reduce the number of switches between components. The field banks are voluminous, so tunable filter allow us to make compact filters. There are different tuning elements that can be used in CU technology. For example, section of ferrite, inserting a small piece of ferrite and apply a direct current, and we can change the inductance and so the resonance frequency of the cavity. Also, pin diode can be used, applying a DC current elements can be switched on off, and so make a reconfigurable filter. For the varactile diodes, we apply a DC voltage to change the capacitance and so the resonance frequency of the cavity. There are also the empty rings connected or disconnected to ground, and for example, also capacity post allows us to make a reconfigurable filter with a high quality factor. We can use also RF MEMS capacitors. MEMS technology has been expanding extremely in the recent years. The capacitor can be very compact with very high quality factor, so extremely low loss and high linearity, especially when they are compared with varactors. So very high quality factors can handle high range and voltage swing. But they have some problems, like they have to be in a hermetic package. Sometimes they need high voltage to drive in, but there are incredible efforts research in this time. So here brief research on the tunable filter world market. The global RF tunable filter market is expected to reach to $203 million by 2023, as investigated by Market and Market, with a compound annual growth rate between 8.86 and 12%, as investigated by Research Market. Most of the market is in North America with 40%, Asia with 30%, and Europe with 25%. This data includes all the world of tunable filter, so the various application. The growth is expected to be on average higher for the space and the defense application. So here the research topic of my PhD include novel planar rebuild technology for passive components, miniaturized and low loss filter in situ technology, and the possibility to design reconfigurable filter using tuning elements like varactor or functional materials. So in the next slide, I show one of my work published in the micro workshop filter in Perugia this year, entitled Miniaturized Ultra Wideband Bandpass Filter based on substrate integrated quasi-lamped resonator. In this slide, we can see the basic structure of the quasi-lamped substrate integrated resonator. And as we can see, there is a rectangular patch that is isolated from the top ground plane through a capacitive gap. The patch is short circuit to the bottom ground plane using a plated via hole. And if the thickness of the substrate is much less than the wavelength divided by 4, as is often in this case, the inner hole and the cavity walls behaves as an electrically short embedded transmission line with of length equivalent to the thickness of the substrate, with the thickness of the substrate. No, wait. There are two ways to control the resonance frequency of the resonators. One is by modifying the capacitive gap and then increasing or decreasing the capacitive value of the resonator. The second one is by modifying the inductive value by changing the diameter of the via. The minimum value is limited by the manufacturing process, and the further compactness can be achieved by adding an extra capacitive long to the basic structure. That's why SMD capacitors have been connected from the resonator patch to the adjacent ground plane. In this way, we obtained an additional degree of miniaturization and the possibility to post-manufacturing tuning the filter response and adjust it in the case of the dimension due to the manufacturing tolerance process change. In this slide, we can see the coupling that we implement for this kind of structure. The input-output coupling here in the left has been implemented by means of a coplanar penetrating probe, as penetrating the capacitive gap of the first class resonator, and the insertion length of the probe enable to control the coupling level. The closer we get to the inner hole, stronger is the coupling. And this value can also be boosted by mounting the SMD capacitors on the top layer. The external quality factor can be extracted using the known approach based on the group delay response. And the SMD capacitor allow us to have a higher coupling. And for the inter-resonator coupling, due to the huge bandwidth required, a strong inter-resonator coupling is required. Moreover, to introduce transmission zero that improve the selectivity of the filter, we used a mixed coupling approach. And the capacitive coupling is provided at the top layer by controlling the distance between the resonator patch and also by mounting SMD capacitor between the actuator resonators. Again, the largest capacitive contribution is made by these SMD capacitors, while the gap, by increasing it, we can finally decrease the total equivalent of the capacitive coupling. And for to implement this mixed coupling, we used a multi-layer technology because we can't put the short circuit on the top layer. And as we can see here in the last graph, when the short circuit is in the upper inner layer, the magnetic coupling dominates. So by increasing the SMD capacitor, we subtract value from the total equivalent coupling, and then the coupling coefficient decreases. But when the short circuit is in the lower inner layer, the electromagnetic contribution is weaker. So the capacitive coupling dominates, and in this case, when we increase the capacitors, we directly increase the coupling coefficient. Here we can see the filter specification. It's a fourth order filter centered at 5.35 gigahertz with a huge bandwidth, 2.9 gigahertz, with fractional bandwidth of 54%, and a minimum in-band return loss of 15 dB. The device must provide a reception higher than 30 dB at the lower stop band and higher than 20 dB at the upper side. It has been implemented in the 4-layer PCB stack-up with a core in Roger and 2 prepreg layers also in Roger. Both internal and external conductor copper layers have a thickness of 17 micrometer, and the total dimension of the structure is 7 millimeter per 7 millimeter. The capacitors used was from AQP, and the performance are summarized here in the table. As we can see, when the size of resonance frequency decreases when we increase the frequency. So, for example, at 2.4 gigahertz, and were measured that's for value of 0.6 picofarad. So when we increase the value of the capacitors, the self resonance will decrease, and and also the quality factor decrease. So we are limiting the total quality factor of the devices. In this slide, we can see the filter design. We use the classical approach of inverter coupled resonator filter, and an equivalent circuit has been implemented, including the lumped capacitor for resonant frequencies, input, output, and inter-resonator coupling control. The value of the old capacitor has been firstly optimized at a circuit level in order to satisfy the specification, and then improve the rejection by properly locating the transmission zero. The structure, as I said, is about 7 millimeter per 7 millimeter square, and shows a huge degree of miniaturization as C-band. Here we can see the filter result and a photo of the fabricated device. Experimental results are here in the figure, and insertion loss at center frequency is 0.75 dB, while in band return loss level is better than 40 dB. As we can see, we have a slight frequency shift, resulting in a higher bandwidth without losing in insertion loss. This is in red, and this one in red is the tested one. And in the black one, we have the one obtained by back simulating using an equivalent circuit model, and extract the actual values of the loaded capacitor for each resonator. So we could get back the measure report. So the measure report can be recovered with a very good agreement. And we had that the deviation from 25 to 150 femtofarad of the capacitors. So we can correct the response and then satisfy the specification. In this slide, there is another example of filter we worked on, and this is a filter with the electronically reconfigurable response. And I mean, the result of the work are not published yet. We use varactor diodes as tuning elements to validate the concept. We manufactured a second order filter. The bandpass filter response is centered at at the various, we had a shift of a range of frequency tuning from 4.6 to 3 gigahertz, and the bandwidth were from 200 to 800 megahertz. And in the figure shows the schematic of the second of the filter. As I said, the varactor allow the tuning of the center, the resonance center frequency of each resonator by controlling, of course, the capacitance, and of course, and also the control of the coupling elements. Bandwidth and central frequency can be both tuned by controlling the voltage biasing of the varactors, and we had to design also a bias network to include it in the PCB. So here the conclusion, I explained a SIV technology, the reconfigurable filters, one example of a miniaturized ultra-wideband filter using SMD capacitors, creating an extremely compact structure. We introduced mixed coupling to introduce transmission zero, and also one example of electronically reconfigurable filter that still has to be polished, so that's why I didn't